They say, oh my God, I see the way you shine. Take your hand, my dear, and place them both in mine. You know you stopped me dead while I was passing by. And now I beg to see you dance just one more time. Ooh, I see you every time.
Hello, good day everyone. Today we are going to continue our discussion with this reinforced concrete design, and this is just a continuation of my previous lecture video of the subject. And before we proceed, so don't forget to subscribe to my YouTube channel, and you may also click the notification bell so that you can be notified if ever I will upload future videos regarding the subject. And now we are going to proceed directly to this sample problem number 3, in which this is just almost similar to the sample problem number 2 in the previous lecture video, but the difference there is this T-beam is just inverted here, as you can see in this figure 1. So if the T-beam shown is uncracked, okay, calculate the stress in the concrete at the top and bottom extreme fibers under a positive bending moment of 108 kN. And if the Fc prime is 20.7 megapascal and normal weight concrete is used, what is the maximum uniformly distributed load the beam can carry if it is used as a simple beam with a 7.32 meter span without exceeding the modulus of rupture of the concrete? Okay, so try to remember if the bending stress is less than the modulus of rupture, so the T-beam is uncracked. So you can check this one later if this is true. But if ever your bending stress is exceeded or greater than this modulus of rupture Fr, so that would probably the beam or the T-beam experiences this crack or cracking. Okay, so this is our dimensions, the width of the flange, the thickness, and we also have the width of the weave, and we have also now this dimension of 69 centimeter from this point here until this point of the weave. Okay, so proceeding, so we have now this simple illustration here, and we take this one as our reference, the x-axis here, and then this would probably be the centroid of this web section, and probably this one is also the centroid of the flange section. Okay, and we have now these dimensions here. Okay, and proceeding, we are going to locate the centroidal axis, okay, using the Varignon's theorem, and by that we are going to use now this formula, the total area times the y bar equal now to the summation of the area times their y, and which is equal now to, in this case we have two areas, so we have area 1 times y1 plus the area 2 times y2. Okay, and this would be now our area 1, this width section, the web section, and we have now this area 2, the flange section. And proceeding, we have also now this y subscript 1 as the centroid of area 1 with reference to this axis here. Okay, and we denote this one also as our y sub 2, which is the location of the centroid of our area 2 with reference now to this axis here. Okay, And now we are going to use now this formula where the area total, no, is just the sum of area 1 and area 2. Okay, so for area 1 we have now this width 31 and the longer side is 69, so we have now this 31 times 69. And for the area 2 plus 152 times 13, so we have here 152 here times 13, okay, times the y bar, and this is equal now to the sum of this e1 y1 plus e2 y2. So for the area 1 y1, so we have here 31 times 69, times the y1 is just the halves, of this length here of 69. Okay, so that is why 69 divided 2 plus the area 2 is we have this 152 times 13, so we have here, and then this will be now our y sub 2. Okay, this 69 plus the halves of 13. So how we get this? Okay, so here this is our y2, so from here to this point is we have 69 plus the halves of this 13, so that is why 69 plus 13 over 2. Okay, so we are done with this formula, and we can actually calculate now the value of our y bar, which is just equal to 54.19 centimeters. Okay, so each location is probably here, in this yellow color. Okay, so this is the location, and this is our centroid, centroidal point, and we can make a centroidal axis here. Okay, and this is now our y bar with reference to this line here. Okay, on top of the wave section. Okay, so after that we are going to calculate the moment of inertia using the transfer axis theorem. So as we can have now this formula for the I sub j, which is equal now to the moment of inertia jx plus your transferred moment of area, which is denoted by this ad squared. Okay, so in this case we are going to apply this one here. Okay, and then we have now this calculation. So our gross moment of area is just equal now to, take note, this is 1 over 12 times the width b times h, so in this case for area 1 over 12, our b here is 31, so that is why 31 here, and we have 69 our h here for the area 1 cube plus area, so each area is 31 times 69 times the distance, this word, this d is just the distance from the centroid of this area 1 to this y bar. Okay, so this is probably our distance, and we can denote this one here, from this point, so from this point we can actually denote it here as our, this is our distance 1. So since we are considering area 1, so this distance 1 is just the difference of your y bar minus this y sub 1. So as you can see it here. Okay, so y bar is equal now to 54.19, so we have here 54.19 minus this y sub 1, so our y sub 1 is just the halves of 69 over 2, and that is why this is 69 over 2, and then we put this here into bracket and raised to the square. Okay, so proceeding now to the second area, so probably for the second area this would be our, so we will change this one. For our second area we will have now this distance here, here from this point until here, so this is our d sub 2. Okay, so before proceeding to this d, so we have to calculate 1 over 12 b h cube. So our B here is just this 152 centimeter side, and our h is just this 13 centimeter raised to the cube plus the area of 152 times 13, and then this D, no, is referring now to this D2, which is just equal now to get this D2 is just the difference of this y sub 2 minus this y bar. Okay, so how much is our y sub 2? This y sub 2 is just equal now to 69 plus halves of this 13, so this is just 75.5 minus the y bar, which is 54.19. Okay, and we raise this one here to the squared, and then after calculation we got this value of our gross moment of area equal now to 0.026030292 rather, no. Okay, so 0.02603092 times m raised now to the fourth. So this is our gross moment of inertia. Okay, so after this one we are going to calculate, no, the stress, no, in the bottom and top fiber of this beam. Okay, so proceeding now, so calculate the stress in the bottom and top fiber under the given moment of 108 kilonewton meter, and this is given in the problem, and then we can calculate, no, from our flexure formula. F bottom is equal now to mc over I, and then our m is just equal to 108 kilonewton meter, and since we are considering the bottom, no, so this is our bottom side of this inverted T-beam. Okay, so we will consider its distance, no, to the centroidal axis, which is 27.81. So that is why we take this one as our C. Okay, since we are considering the bottom, so the distance, no, from this bottom fiber, no, of this inverted T-beam to the centroidal axis, which is 27.81. Okay, so that is why we have now this value here. So 108 times this 27.81, no, so we will use a unit of meter here, so that's why we have this 0.2781 all over this I, no, this I is just equal now to the gross moment of area, no, which is just equal now to 0.0260302, and the unit here is m raised to the fourth. Okay, so if you are going to calculate this one in megapascal, so we have now this result, no, of 1.15 megapascal. Actually the unit of your moment here is kilonewton meter, and this is meter, so kilonewton meter squared over this m to the fourth. So its result is kilonewton per meter squared. We have to convert this one into megapascal, no? So you are going to divide, no, the result of this one, you are going to divide with 1000 to make it into this megapascal unit. Okay, so the result is 1.15 megapascal for the bottom, no, the bending stress for the bottom part of this inverted beam. So how about the top, no, the top portion of this inverted beam here? Okay, so here we are going to use, no, this y bar because its distance, no, from the top of this web, no, to the centroidal axis is denoted by this y bar, so that is why we use this y bar here, which is equal now to 54.19 centimeters. Okay, and then after that one we are going to use the same moment of 108 kilonewton meter, and gross area of this section equal now to this 0.0260302. Okay, so substituting those values here and calculating and converting the result, no, into megapascal, so we have now this 2.25 megapascal for the top bending stress of this inverted T-beam, and this would be now our answer for this. Okay, and after this we are going to calculate, no, the maximum uniformly distributed load, no, denoted by this small w, that the beam can carry without exceeding the modulus of rupture, no, according to the problem statement. Okay, so we have here, no, we are going to calculate the maximum uniformly distributed load, but first we need to determine first the modulus of rupture. How much is our modulus of rupture, denoted by this F sub R? So this is given, no, and this is also found in our NSFP code of 2015, which is just 0.7 of your lambda, where we use 1.0 here because this is for a normal weight concrete, and our FC prime is given, which is equal now to 20.7 megapascal. So our result here will be in megapascal. So our FR is just simply equal now to 3.18 megapascal. Okay. So try to observe, no, the bending stress, no, at the bottom and at the top of this inverted T-beam. As you can see, this F bottom and F top, no, are all less than the modulus of rupture, no, of 3.18. So what is the indication of this? So this means that the flexural member did not crack or do not experience crack or cracking. So that is why in the problem statement, no, that we are going to assume that the beam is uncracked, and now we are confirming that the said inverted T-beam did not crack or do not experience cracking, and this will verify, no, that statement there based on the result of our bending stress, no, for this bottom and top of this inverted T-beam compared now to this modulus of rupture FR. Okay, so now we are not yet done, no, so we are going to determine the uniformly distributed load, no, and we need to calculate first the moment, no, and we term this moment as this cracking moment, MCR. Okay, so from here we have this formula of FR times gross moment of area over this Y subscript T, in which our Y subscript T, no, as you can still remember, this is now the distance, no, from the centroidal axis, no, to the extreme fiber in tension, no, as you can still remember in lecture video number 1. So our extreme tension fiber or tensile fiber is located, no, here at the bottom. So that is why our Y sub T is just equal now to the C, which is also equal now to 27.81. So take note of this one. This Y sub T is the distance, no, from the centroidal axis to the extreme fiber under tensile or tension. So that is why this is in tension, okay, and this is in compression. So we are going to concentrate here na in tension. So that is why we use 27.81 for our Y subscript T. Okay, and then substituting the calculated FR, which is 3.18 megapascal, and we need to multiply this one by 1000, no, to make it into kilopascal, times your gross moment of area, which is 0.0260392 m to the fourth, all over this C or Y sub T equal na to 27.81. Okay, so our unit here is in megapascal, no, so we need to multiply by 1000 this FR to make it into kilopascal, and then afterwards we can have this value with this unit of kilonewton meter, no. So our moment or cracking moment is just equal now to 297.66 kilonewton meter. Okay, so we are not yet done, no, so we are going to calculate, no, the uniformly distributed load small w, since this is a simple span. So we will use, no, this basic formula for simply supported beam in calculating the moment or this cracking moment, which is equal now to WL squared over 8. So we have M, which is equal now to this MCR, and this L, which is equal now to 7.32. So we can get this uniformly distributed load W, no. So calculating So we can arrive to this value of 44.44 kilonewton per meter. Okay? So as you can observe in previous problem, when this T-beam is not yet inverted, the uniformly distributed load is almost doubled if the beam is oriented the opposite way. So this value of 22.81 kilonewton per meter when the T-beam is not yet inverted in our previous lecture, which is the sample problem number 2. But when it is inverted now, in this case, so its value is 44.44 kilonewton per meter. So it is almost doubled. The uniformly distributed load is almost doubled if the beam is oriented the opposite way. Okay, but a reminder to everyone that this should not be the case always, because don't get the impression that this is the best orientation for a T-beam, because when we are going to examine reinforced sections in our future discussions and videos, so the opposite will be true. So you have to watch for it, abangan nyo yan sa susunod na mga videos natin. Okay, so that would be it for this lecture video today, and I hope that you learned something out from this video of mine. And for our next topic, we are going to discuss seaboard exam problem number 1, and we are dealing with this working stress design. So abangan nyo rin to in our next lecture video. And before we will end this one, I would like to cite my references here. These are my references, and thank you very much everyone for subscribing, and thank you also for watching and listening, and see you next in my lecture video. See you in my next lecture video. Okay, so thank you and have a pleasant day everyone. God bless and keep safe everyone.